Now, our current simulation is looking pretty cool, but as I've mentioned, there are some kind of glitchy spots where we have some exploding grains that are shooting out from the body here, and there are a couple other improvements we can make while we're here as well. And one of those improvements is actually a pretty quick fix, and if you take a look at the grain particles, the way they're point deformed to follow the animation, you can see that we kind of have some gaps, and the grain particles are sort of clumping around these little tentacle ridges there. A bit more visible if we look at this in the actual viewport. And this is not what our initial grains look like. If you look at the grains just before the point deform, you can see we have a nice solid tentacle shape here. It's just the point deform stage that's causing these splits in how they're following the animation. And the reason for this is because we don't have a whole lot of resolution on the tentacle tubes between the ridges. So as this mesh is deforming the grains, they're really mostly just driven by these ridge shapes because there aren't any more divisions on the tentacle tubes in between to interpolate that point deform nicely. So a quick fix for this is to just make our subdivide affect the tubes. So we already have a subdivide on the tentacle ends here to improve the point deform there. If we just go to the group on this subdivide here, we can update this to not only subdivide the ends, but to subdivide anything that ends in tubes as well. So after creature tentacles ends, just put a comma and then */tubes with no spaces in here at all. Hit enter, and now any objects with a path attribute ending in tubes will also be subdivided. And let's copy the comma *tubes, and let's do the same thing to our rest position as well. So if we display the subdivide and the rest pose as before, we have to make sure that the topology of this matches our animation topology. So the same changes are required here. Just paste the comma */tubes into this subdivide as well. Now that's nicely subdivided, and if we display our point deformed grains, now you can see that they're no longer clustered into those ridge areas, and everything is maintaining this nice kind of smooth tentacle shape all throughout. And now to fix the issue with the grain particles exploding, particularly in this body area here, this can be a slightly more difficult type of problem to figure out sometimes. The fixes for this aren't always totally obvious. In this particular case, I did try turning off the mass shock controls in our Vellum solver. So going back to the Vellum solver under Advanced and Grain Collisions, I mentioned in a previous video that when this is disintegrating in mid-air, we don't really need this mass shock anymore. But this didn't really help out the simulation at all when I tested with that disabled, so we have to look at other solutions for those exploding sections. And I think in this case, the big problem here is probably that the body is deforming on this creature, and when these grain particles are following this bending and deforming creature body there, it's causing some of these grain particles to intersect each other in the middle of this mass. So there are a couple things we can do to address this. One thing is to use a point relax on the grain particles to prevent intersections between them. And it looks like we don't have many grain particles intersecting on the surface here, so you might not see an obvious visual difference when we apply this relaxation, but let's see what it looks like anyway. And you could do this before or after the trail sop. I'm going to do it after the trail because the relax is actually kind of a slow operation when you're doing it in 3D space with a lot of particles. And because the trail sop will evaluate not only the current frame, but the frame before and or after, depending on how your velocity computation is set, this can require the relax to be computed more than once if you put that before the trail, and that can really slow things down, which is why I'm just putting it after the trail, so that on each frame, we only need to compute this point relaxation once. So let's turn on relax in 3D space. And this is using the p-scale to determine the size of each point, which is already set correctly on all of our grains here. Point radius scale, I'm just going to leave that at 1. And for max iterations, this just determines how many times it'll run this process to relax the points and avoid intersections. Let's try leaving it at 10 and see how that looks. And because this can be a slow process, I'm going to use the performance monitor to see just how much of a computation hit it is to do this point relaxation. So this is kind of a slow process. This is taking over 30 seconds per frame to relax all these points. And because this is a bit slow, that's actually, I think, slightly slower than the Vellum computation of the actual grain simulation. So we might want to cache out these relaxed points before the sim so that we can just read in that cache and we don't need to always keep performing this relaxation and in the process make our sim significantly slower. And another thing we could do on this relaxation to speed it up and perhaps preserve our shape slightly more closely is to turn down the max iterations here. When I switch between displaying the relax and the trail, you can see we are getting some inflation from those grains being pushed out a bit. And turning down our max iterations from 10 to 5 does make things process a bit faster, and it does reduce the amount of change in the overall shape of these grains a little bit. So you may need to play around with the right number of max iterations to fix intersecting grains versus the speed of that computation and how much it changes the shape. I'm not too worried about some shape change here because we're only going to see the grains once they start disintegrating. We're not going to render any of these grains before they become active. So it's not really a problem if they do expand a little bit, but it's still nice to not change the shape any more than really necessary. So before we cache out these relaxed grains, there's another thing we could do that could optimize our overall sim a bit, and it could reduce the potential of some of the overlapping grains in here. And right now, the entire body of this creature here is completely filled with grains all the way through the center of it. And we could hollow out this a little bit so that we don't have this entirely filled with grains. We can give this a bit of an empty core. We do still want to have a fairly thick amount of grains coming in from the outside of the surface because we want this to feel like it has a decent amount of mass as it disintegrates. But we can hollow this out a little bit for some optimization, and also any issues we have with the grains intersecting will be most severe furthest from the surface. So if we display the surface that we're using to drive the grain animation, I guess it's kind of hard to see in wireframe there, but the grains close to the surface will match the animation pretty closely. But the further you get from the surface, the more this point deform could be a bit of an approximation of where those grains need to go. So the grains being pushed around inside the center of this body here seem like they may have more potential for being pushed into overlapping positions with each other versus the grains closer to the surface here. The ones on the surface should respect the animation a lot better without nearly as much potential for overlap. And to create that hollow center inside our grains here, we can do this with an SDF that has the center of it cut out. So going back to the creature scaled rest before the grains are created, I'm going to just convert this into an SDF VDB. So let's drop in a VDB from polygons, connect the creature scaled rest to that, and it looks like this 0.1 resolution gives us plenty of detail for creating these grains. We could try to get a bit more detail in there if we want to. For example, all of the tentacle ridges seem to be kind of combining with each other at this resolution, which isn't necessarily problematic, but we can see if that improves if we decrease the voxel size a little bit for more resolution. That's a little bit better. Looks like 0.05 still gives us reasonable enough VDB performance and a bit of a better representation of those tentacle shapes. So now that we have this SDF for the entire creature here, let's create a hollowed out region that we want to cut out in the middle of the creature body. So I'm going to start by just isolating the body from the creature scaled rest. So I'll create a new null off to the side here, and we'll do a selection based on the path attribute. And let's select the main body, and I'll select these seams as well. Then we can blast this away, and on that blast, flip it to delete non-selected to isolate just those sections that we just picked. And it looks like we need the eye mount as well. So if we hit this little arrow next to the group selection, that'll go back to let us add things or remove things from the selection. So I'm just going to shift select this eye mount geometry as well, and then hit enter, and that will update our group selection on that blast. So now let's see if this looks like it has any obvious open shapes. It looks okay. So I'm just going to convert this to a VDB as well. So let's copy our existing VDB from polygons and paste that underneath this isolated body section here and connect that to the blast. So now we have a decent looking SDF just for that body region. And now we can use a VDB reshape SDF to erode this shape to create just a section in the center of this that we want to hollow out from the full VDB. So that VDB reshape SDF will default to doing a dilation that's expanding our VDB a bit. So instead, let's flip this to erode, and we may need to do a fairly high erosion for this. Let's try a value of 10. Looks like we need to go significantly higher with this erosion. 100 is a little bit too extreme. It's not giving us nearly enough of a core there, so let's just try something in between. 50 is looking pretty decent. I think 60 is looking like a pretty decent starting point for an amount to take out of the center of that body. So let's move up our creature scaled rest, and we can do a VDB combine to subtract this hollowed out area. So drop in that VDB combine, connect our full body VDB to the first input, and this hollow section into the second. And that VDB combine operation will be set to SDF difference to subtract the second one from the first. And this result may be a little bit hard to see just from the outside, but if you zoom in, you can see that cutout shape represented in there. So I'm just going to create a null here and call this creature hollowed volume, and then connect that to the first input of our vellum constraints grain. And this is visually hard to see what's happening because this whole space is filled up with grain particles, but we can check this to make sure that it's doing the right thing and correctly hollowing out that center. So I'm going to use a clip sop just to delete a portion of these grains. On that clip, let's flip that to the x-axis. So change the direction to 1, 0, 0. And it looks like we're not getting any hollowness in our initial grain creation. So something must be happening here where when it creates these initial grains from a volume, it's not just using our SDF as it is. So instead of building our initial grains from this hollowed out creature, we can just connect the grains back to our creature scaled rest and then delete some of these central grains afterwards. So we can just delete the section that's creating the hollowed volume, and then we'll use just the hollowed portion to delete those points. So after our vellum constraints grain, let's create a group sop, and the group name will be hollow. Group type is points. turn off the base group, turn on bounding regions, set it to bounding object, and I'll create a null to indicate that this volume is our hollow center, and connect that to second input of our group SOP, and drop in a blast, select the hollow group, and display that. And we can't really see what's happening because it's just deleting points that are in the middle of the body that we can't see. We can kind of check this by saying delete non-selected. So this shows us the grains that are actually being removed. So that looks correct. So flip that back to delete the selected stuff. And we no longer need this hollow group. So on our blast stop, we can tell this to delete unused groups to clean that up. Then I'm going to copy paste this to do the same thing on the vellum constraints second output there. So just copy that group, connect the second output from our vellum constraints grain to that, and we'll drag this other wire from that second output to connect to our blast that's doing this hollowing, and keep things nicely organized, because that's always good practice. And let's also take a look to double check what we're deleting on our constraints output here. As before, we'll check this to delete non-selected to make sure we have this one set up correctly as well, so this looks correct also. I'll turn off delete non-selected, and I'm just going to double check to make sure that we have the same number of points coming out of both of these blast stops. So the number of constraint points here does correctly match the number of grain particles here. And you can see we've gone from over 520,000 particles down to 473,000. So this will give us a little bit of a speed up on our relax process on the simulation itself, and can reduce some of those potential grain overlaps in this hollow area here that could have been causing some of the problems we were seeing with parts of our sim exploding. So now with this hollowing set up and our relaxation set up, which I think I will turn up to 10 just to help ensure that we're getting sufficient relaxation there, we can now drop in a file cache after the relax. I'll call that cache relaxed grains. And for the start and end points of this, we don't need to run this on the entire time range. We only need to cache out the relaxed points from the starting point of the simulation through the point at which they're all activated, because once they're all activated, we don't really care about the positions of the animated input since the sim will have completely taken over. So if we go back to the solver where we set up the infection growth for that activation, we can copy the relative reference to the start and end frame here. So we've already decided we're running our activation solver from frame 95, which is the start frame of that solver, up through 160. So let's just copy that parameter. And then on our file cache for the relaxed grains, let's paste the relative reference in here. So this is now set to run from 95 to 160. And I'll put this cache in job/geo disintegration, make a directory called relaxed grains version 1, and then I'll call the cache relaxed grains.$f3.bgeo.sc, and accept that, turn on load from disk, and then finally we can cache out these relaxed points. Now after caching the relaxed points and rerunning our grain simulation, we have something a lot cleaner and a lot nicer like this. And we still do have a few grains exploding at the very end there, but overall the result is working much better. And in addition to the problematic explosions that we had in the body area before, the tentacles were also kind of exploding as well. So if we take a look at the previous version, you can see that the tentacles are really exploding apart, and it doesn't actually necessarily look bad because the explosiveness of those tentacles coming apart is kind of cool, but it's always best when we do that stuff on purpose instead of just relying on the sort of system exploding and the little bits of instability to give us the desired effect. Even if it looks cool, we really want to kind of control that stuff more intentionally. So this kind of messy and broken simulation is much improved by our latest changes, with the hollowing and relaxation and the mass shock being turned off. So the last tweaks that we need to make to this are fixing that one little explosion at the end, and also perhaps inheriting more velocity at the end as well. The velocity inheritance looks alright on the tentacles. I suppose we could use a little bit more velocity inheritance there, but then as the erosion reaches the main body in the very front of the character here, it makes it look like its motion stops kind of abruptly, and I'd really like to see a bit more continuation in the direction of the creature as that disintegration is finishing there. So we can ramp up our velocity inheritance toward the end of the sim, and once we do that and fix that last little explosion at the end there, then things should be pretty well sorted for this simulation. In terms of the velocity inheritance, I'm going to increase the amount of velocity inheritance we have on the tentacles by a little bit, and then by the end of this simulation, as the disintegration reaches the front of the creature, I'm actually going to try overdriving the amount of velocity inheritance. So if we set the multiplier to something like 1.5, then we're actually going to inject a bit more of the directional velocity than the original animation has, which could potentially look kind of cool. But before we do that, I'm going to try to fix this explosion that's happening at the end of the sim just by clamping down on the velocities. And this is something that you may need to do in many different types of simulations in Houdini. This is also very common, for example, in rigid body sims. Most of the time I find myself setting speed limits on RBD pieces to avoid erratic pieces getting thrown really violently like this. And it's also a useful tactic here. So let's start by checking the speeds that are currently in the simulation. So if we go to a frame where we have a fair amount of motion happening already, but no exploding particles, maybe anywhere in this range here should work fine. Let's try 175. I'm going to drop a wrangle after the DOPNet, connect that to the DOPNet, and I'll call this speed check. And I'll select my speed check preset from the gear icon on that attribute wrangle there. So the speed from velocity just checks the length of our velocity vector to set a speed attribute. Now if we check our speed values and the attribute spreadsheet and sort by the speed attribute column, we're actually getting some nans which could be a bit alarming. And on the high end, we're getting 7 to the 15th power, which is an extremely high speed value. That's not something we would expect for this simulation, and an indication that something is behaving erratically or is broken. And we can often fix issues like this just by setting some speed limits in the sim. And many different types of simulations typically require this. For example, for rigid body sims, I'm always setting some speed max or acceleration max, and that can help us a lot with these grain sims as well. And we can get a sense of the typical speed values just by scrolling through the spreadsheet here, and that might be enough for you to decide where you want to try setting your speed min and max, but it can also be really helpful to use a blast stop to visualize this in the viewport. So if we drop in a blast and display that, and in the group type at speed is greater than 10, and then set the group type to points because speed is a point attribute, you can see that when we toggle this to delete non-selected and back, it looks like about half of our grains have a speed greater than 10. So then we can just increase this threshold to see what sort of speed range encompasses most of the natural behavior of our grains. So let's try 20 and 30. And it looks like there's not a big change from 20 to 30. If we flip this to delete non-selected, it looks like a speed limit of 30 encompasses all of the normal motion of the grains that we're seeing here. So then back on the DOPNet, let's rewind our sim and dive inside here, and we can set a pop speed limit on our vellum grains. And I'll drop this below the pop wind there. And I'm going to set both a minimum speed and maximum speed. Our grain particles should always be moving at least a little bit, and this probably won't have much of an effect, but we could say that a minimum speed of just 0.01 makes some sense for this sim. And for the maximum speed, let's try a value of 30. And before we rerun our simulation, let's also change the velocity inheritance so that when we get to the end of the sim, the grains continue in the direction of the creature's animation. As I mentioned before, it looks like these grains kind of stop abruptly once they get to the creature's head there, and it would be a lot more natural if they continue in the path of that motion a bit more. So on the sim attributes wrangle here, let's animate our velocity multiplier. And you can set keyframes on here if you want, but I often prefer to just use a fit function when I want a linear progression on this parameter. So I'll say fit the current frame number from frame 95, and then let's pick the frame where this progression completes on the front of that creature there. It looks like it's finishing around 145. So we could say by the time it gets to 140 or so, it's achieving maximum velocity inheritance. So fit the frame from 95 to 140, and we'll start with a velocity multiplier of 0.25. And I'm going to ramp that up to a multiplier of 1.5. So the velocity that it's inheriting is actually 50% more than the velocity in the actual animation to kind of throw those grains forward a little bit. So now with those speed limits applied and the velocity inheritance updated, let's run a new sim and see how this looks. Now unfortunately, our new sim isn't looking much better with the velocity inheritance changed and the speed limits applied, but the things that I did find fixed this simulation were, number one, just changing the substeps on the vellum solver up to 10. So sometimes these exploding things, especially with grains, just need some more substeps. It's good to troubleshoot some other potential problem areas first so that you don't always just crank up your vellum substeps anytime you have a problem. But after looking at the other likely causes, it's totally fine to just crank these substeps up quite a bit. So I found the main thing that fixed this sim was turning those substeps up to 10. And I also found that it looked like there was something strange happening with the velocity inheritance. It doesn't look like it's quite picking up the correct directions here. And there's this thing that happens in Vex where if you have a function that can return multiple data types, like the point attribute lookup that we're using to fetch the velocity from SOPs inside our SOP solver and our DOPNet here, you can see when we activate the grains, we're looking up the velocity and adding those velocities to the newly activated grains. But this point function can potentially return various different types of data. And in some cases you can confuse Vex and make it assume that the wrong data type is coming in. So what I think might be happening here, and it's not very obvious in the flipbook, but because we're taking a float value and multiplying it by this point value here, Vex might be assuming that this is returning a float and not a proper vector. In which case we would have incorrect values applied to our velocities here. And one thing that you can do to fix this is to just fetch this velocity separately. So instead of doing this all in one statement, I'll cut out that point velocity lookup. And on our if statement, when we want to put multiple lines in here, we need to use curly braces. It's fine to not use the curly braces when you're just using one line of vex with your if statement, but with multiple lines, we need these braces in there. So now we're just going to create a new vector. I'll say anim underscore v and set that equal to this point velocity lookup. And because this vector is being assigned the results of this point function here, that means it's assuming that this will return a vector. So now that we reliably have that velocity fetched to this anim v local variable, we can now put that in to our velocity amount multiplier here, which, is no longer necessary because we have the velocity being multiplied up in SOPs as well, but it doesn't hurt anything to just multiply it by 1 here also. So we're fetching the animation, ensuring that's a vector when we add it to the initial velocities. And I've also found that we need to update our pop speed limit here. When we checked with our blast SOP to see what the speed values in the sim looked like, it seemed like most of the speeds were sitting around 30 or so, but when we're inheriting velocity, we want to make sure that the speed limit allows us to inherit as much of the velocity as we're attempting to. So on our attribute wrangle here, where we're setting the velocity amount to be 1.5 by the end of the sim, that means that our speed limit has to be at least 1.5 times whatever the velocities are in our animated input. So we can move our speed check over here, and we can use that to also check what our animation input looks like. So connect the grains to sim to the speed check. And let's check that spreadsheet and maybe go to a frame closer to where this is completing its disintegration. So I'll try like 145. And if we look at the speed values for our animated input here, it looks like those speed values are ranging from 35 up through almost 200. So when we're inheriting a lot of velocity from the animation, we're going to need a much higher speed max if we want to pick up these values that are coming from the creature's anim. So then back on the pop speed limit, I set the maximum speed to 300. And then I found that the grains were kind of ballooning up a little bit as they were activating around the body. So we didn't really need to overdrive this velocity amount here. So I just turned that down to 1 at the end of that disintegration, instead of overdriving that with 1.5. And now flipbooking this once again, after making those changes, we have a much nicer and more successful result. So here we have a decent amount of velocity being inherited in the sim. We don't have any of those grain explosions now that we've increased the substeps, and everything is looking pretty nice and interesting here. You could certainly go in and tweak some of the various influences on this to finesse the sim, but as I've mentioned earlier, we need to resimulate our grains once we add the tentacles simulation in there, so don't feel like you have to get the sim 100% perfect at this point when we need to resimulate it later. I also went a little bit higher res with my grains than this for my final sim, so it's up to you if you want to try turning up the grain resolution some more, or if you just want to wait for running that modified sim later. And when we're happy with this version of the sim and we want to cache this out for rendering, it's often a good idea to do a bit of attribute cleanup before caching this out. So looking at the contents of our DOPNet here, we have some groups that aren't really necessary, so we can delete those. And in the group delete, I'll just put in star so that it removes everything. And then I'll add an attribute rename to clean up some unnecessary attributes. So the point attributes that we want to keep are velocity and the color. And we want p-scale. And we can keep the sprite attributes if you still want that sprite display preview. And there are more than one attribute that start with sprite, so we can just put in sprite star to grab all of those. If we had an ID attribute, it would be good to keep that one as well, but it looks like we don't. So you can consider adding that if you really want to get in there and do some ID based cleanup later. But for now, I'm not going to worry about it. And sometimes I just like deleting the detail attributes as well, just because we don't really need that var map in there. It doesn't really make a difference either way. And back on the points here, we've specified the attributes that we want to keep, but because the star is still in there, it's going to keep all the attributes regardless of whatever else we've specified. So it's still keeping everything, so we need to get rid of this star as well. So now we have 6 attributes instead of the 36 point attributes that we had before, so this will make our caches on disk much lighter. And now let's cache this out. For the start frame, I'm just going to grab the start frame of the sim, paste the relative reference in there, and the end frame is just going to be 240, and turn on load from disk, and I'll point this to job/geo disintegration. And for this disintegration of the creature where it just has the procedural tentacle animation, I'll call this disintegrate basic.bo1, and the cache name will be disintegrate basic.$f3.bgo.sc. Now we can cache this out, and then we can take a look at rendering this along with the eroding creature, because ultimately we're going to need to merge our disintegrating grain particles with the actual animated creature, and we'll need to blend these together for rendering, and we'll take a look at that in the next video.